rover mission since 2002. He's worked extensively with multispectral PanCam data from both the Spirit and Opportunity rovers, looking at the multispectral reflectance of rocks used by the rover. I know it's hard for me to say these bios because everyone has such impressive bios. At the multispectral reflectance of rocks viewed by the rovers at the Columbia Hills, the Gusev crater, and on the plains and craters of the
Meridiani Plano.
There we go. Yeah, there. He is also involved in several other projects, examining terrestrial analogs of Martian surface materials, working with orbital remote sensing data of Mars, and examining hyperspectral reflectance data over mining sites in western India. In his free time, do you have free time? In his free time, he's an avid rock climber, enjoys skiing, hiking, taking his dogs on walks, and also doing some TV and movie trivia. Maybe I'll get into that a little bit later. Some more drinks, maybe do that. So without further ado, please give it up for Bill Fernandez.
Right.
Thank you.
All right, thank you very much, Lindsay, and thank you very much for having me here this evening. I have a lot of great pictures to show, and hopefully it'll all make sense in the end. I tried to throw a few slides in with spectra, even though people always tell me, "Oh, don't put reflected spectra in the presentation." People won't like that, you know. But I have to tell people that, you know, looking at spectra is my life, and you know, most people then kind of say, you know, kind of that's very sad, but it's true. So let's go ahead and get started. Oops, gonna turn this on. So here is relative sizes of Earth and Mars. Mars, of course, smaller than the Earth. If you're standing on the surface of Mars, you would only weigh about a third of what you weigh here. But and after eating the chocolate dessert there, that we all could wish for that. But don't let the small size of Mars fool you, because the surface area of Mars is approximately equal to the land surface area of the Earth. So there's a lot of territory to explore. So the guiding light of the NASA Mars exploration program for a number of years has been this theme of follow the water, because the idea is to try to understand the aqueous history of water on Mars, because water is believed to be essential for life, and of course we want to try to understand if life ever got going any place else in the solar system. And so this pursuit has taken a number of pathways, including looking at the geomorphology of the surface, and also the landed missions doing in situ research. And just the images that we have here show just a kind of imagination of what Mars might have been like if in fact it did have oceans early in its history. That's still not really clear, but there was a lot of water and a lot of activity of water early in its history. So here's where we put spacecraft down on Mars, and also where we're planning to put one down next year. There's going to be actually it's later this year, the launch of the InSight, which is going to be a lander. But so I'll be talking primarily about Spirit, Opportunity, and Curiosity in this talk. And so Opportunity landed here near the equator. Spirit was about 15 degrees south of the equator, and Curiosity also fairly close to the equator. And this is the relative sizes of both the, these are some testbed rovers. In 1997, we had the Mars Pathfinder mission, and there was kind of a small testbed rover there, the Sojourner rover, so that's the little guy right there. And then this is about the size of the Spirit and Opportunity rovers, sometimes describe it to people as being about the size and about the speed of a Galapagos tortoise, if you've ever seen these things. And this is the Curiosity test bed. The Curiosity rover is quite the monster, so it's really a pretty impressive feat to land that on the surface. I'll be spending most of my time, since I'm more familiar with the Spirit and Opportunity rovers, talking about these two, even though the new flashy kid on the block is Curiosity. But so this is the instrument payload that we had with the Spirit and Opportunity. They're both identical, the identical payloads. And so we have a kind of remote sensing package, this multispectral and stereo camera, the PanCam, had a thermal emission spectrometer, which is this mini test. I have a robotic arm, which has several instruments on it, a microscopic imager, an alpha particle X-ray spectrometer, which measures chemistry, a thing called a Mossbauer spectrometer, which is sensitive to iron mineralogy, and a rock abrasion tool for actually grinding into the rocks. And just a little bit, since you guys are astronomers, and some of you probably do some astrophotography, I thought maybe I could throw some instrument jargon at you. So here's the PanCam, which is the PanCams, which have two 1024 by 1024 CCDs. And remember, these things were designed in the early 2000s. So, I mean, this is kind of old technology now, but I mean, it was pretty cool at the time. So, and they have two 8-position filter wheels, so we can get the multispectral imaging. And this just shows has 11 unique spectral band passes, and so folks like me are really interested in trying to identify materials on the surface of Mars based on the way that they reflect light. And so even with these just 11 spectral bands, we're able to do quite a bit, able to distinguish kind of ferric oxide minerals from more ferrous or iron 2+ minerals. And so you can see the dots here represent the band passes of the PanCam. And also this mini test instrument, which unfortunately is not working anymore in Opportunity. It was quite a nice instrument for measuring the detailed spectra, just point spectra in the thermal infrared. And the thermal infrared is really good for doing geologic remote sensing, because a lot of minerals have fundamental absorption features in the thermal infrared. And so this is kind of an overhead looking down from the top of the mast, kind of selfie, if you will, of Opportunity. And one thing I might point out is just the fact that the soil is dark here. The Meridiani Ponum, the place where the Opportunity rover was targeted, it was one of the dark areas on Mars. Of course, you guys have probably all looked at Mars through the telescope, and then Mars has bright regions and dark regions, and the polar caps. So Opportunity was the first rover to go to one of the dark regions of Mars. And this is a deck pan or selfie of the Spirit rover, and of course what you see right away is how dirty the solar panels are. So the Gusev crater site where Spirit landed is a much more dusty place, and very, very fortunately, Mars is also a windy place. So even though we would get these periods of time when the solar panels would get really coated with dust, generally would get at some point with both rovers would get some kind of wind storm which would blow a lot of the dust off and restore the solar. And they are solar panel powered rovers. The Curiosity rover has a RTG, radioisotope thermal generator, where it gets its power from, but both Spirit and Opportunity depend on solar power. It's kind of much like Frankenstein's monster, right? Where he was like supercharged with electricity, so he kind of kept going and going. So it's kind of like what's happened with the Opportunity as well. So this is an orbital view of Gusev crater, this site where we targeted the landing site for the Spirit rover. It's about the size of Connecticut, I think, and the reason we put it in here because there's a channel that emptied in here, and we thought that there might have been a lake there in the bed of a Gusev crater, and so we're trying to again understand the history of water. So this geomorphologic evidence for water in Gusev crater was fairly strong, and this shows where the landing site was in Gusev crater, and then what happened was that we decided to drive to this site, the Columbia Hills, which is kind of a more ancient part of the crust, which is kind of sticking up through the volcanic plains on the floor of the crater. Because what we found when we landed was, in fact, it was covered. It wasn't really, we didn't see any lake bed or lake sediments, what we saw were lots of volcanic rocks, so it was a volcanic plain. But this site, the Columbia Hills, is something that was sticking up through the basalts, and so that was more ancient and did in fact show evidence of water. And this is a more detailed view of the traverse. We called those hills the Columbia Hills in honor of the Space Shuttle Columbia. And in fact, we named some of the individual peaks after some of the astronauts who were on board. And so this hill that actually Spirit climbed, Spirit was the first kind of mountain climber on Mars. It climbed up the height of this peak, which is called Husband Hill, after the Space Shuttle commander, Rick Husband. And then it came down past a dune field and spent a lot of time around this site called Home Plate, which from the orbital imagery kind of looks like a little bit like a baseball diamond. I mean, it was kind of, this happened during the early part of the mission. It was 2004 when both Spirit and Opportunity landed, and there were a lot of Red Sox fans on the team. Very unfortunately, I'm a New York Yankees fan, so I mean it was a little hard to put up with some of those people, but. And this is actually up on top of Husband Hill and looking down towards Home Plate, and so you can see the Home Plate feature right here, and Spirit did a lot of work right on top of the feature and down around this side, and then we were trying to drive to the south on the western side of Home Plate when it got stuck in kind of a sand trap, and that's when we lost contact with it. But this is, I mentioned, a dune field that we went through, and on Mars, the sand that we see, the sand-sized particles that we see are mostly ground up basalt grains. But basalt is, of course, a volcanic rock that we see if you see the volcanoes on the Hawaiian Islands. Those are all basalt, or if you've driven around up like in southern Idaho, there are flood basalts in southern Idaho. So this is the sand-sized particles are all this dark-grained material, and this is a dune field we drove by. And again, drawing the attention to the Home Plate feature, and this is what it looked like as we were driving up towards it. And I also mention here when we're keeping track of the time of the mission, we think it generally in terms of the Sol number. We call a Martian day a Sol. So, and a Martian day is about the same length as an Earth day, but only about 40 minutes longer. And just for the folks who were kind of keeping track of the filters used with some of these things, I tried, at least in some of these slides, to put down which filters were used for the kind of red, green, and blue. So this is red 753, green 535, and blue 482 nanometers. So it's kind of a false color image. And this is when we got definitely much closer to Home Plate. This is what we saw. This is kind of a wide area view, so it's a little distorted. But as you can see, it's a layered deposit of rocks. And in fact, what was really exciting when we got up there, or at least exciting to someone like me, it's like you know, it's some distorted layered rock spill. I mean, what's so exciting? But I mean, it's really exciting to me. So this is what we call a bomb sag. We saw a bomb sag in some of these beds, and so that's something that you see in volcanic ashes that are formed in what we call a hydrovolcanic eruption when water and magma mix. So this is a example of a bomb sag that I took a photograph. I did some field work up at this place, North Minden Butte, up in Idaho, and so when you have these kind of water and ash mixed together, it makes the beds, ash beds, a little more plastic, and so they can deform when kind of a big volcanic rock lands on top of them. And this is just illustrating this much more water than was probably involved in a hydrovolcanic eruption that formed the ashes at Home Plate, but a hydrovolcanic eruption in Tonga in the Pacific. And it generates these types of beds. This is, again, some of the field work. I mean, this good-looking guy and his dog here are exploring these tuff ring beds. Tuff ring is a kind of volcano that's formed from these types of hydrovolcanic eruptions. And so the beds that make up home plate, we think, are these types of beds. Something that is really exciting about what we saw with found at home plate is down here on the eastern side. There were some very light toned rocks, which we see here, and so these light toned rocks, and then also light toned soils, which we dug up with the wheel, because actually at this point in Spirit's mission, the right front wheel had stopped working, so we actually had to kind of drag it along, much like Igor in one of the Frankenstein movies. So dragging along, but this did have the benefit of dredging up the soil. So we saw, in several places during Spirit's mission, we found these kind of light toned soils just underneath the top of the soil, and so, in many instances, these were sulfur-rich soils, but for these soils on the eastern side of home plate, they turned out to be very silica-rich. In fact, this is a APXS spectrum, and this peak here is just silicon. So it's really almost, some of these soils were nearly pure silica. And so how do you get? And then there are also these nodules, which were very rich in silica. There was one that we drove over with a wheel. I think we kind of intended to drive over one of these rocks, but we ended up driving over another, so it was an innocent bystander. So that was how it got the name. We used to have a lot of fun with some of the naming of some of the features, but then some folks on the team took the fun out of it, but you can ask me about that later. But this is one thing that I do on the mission is doing kind of color processing. And the colors on Mars are actually very subtle. Most of these things I'm showing you are false color images. I mean, this is essentially a false color image here, but I do with a lot of the data, I'll apply what's known as a decorrelation stretch, which is kind of a very extreme stretch of the data involving principal components analysis and then stretching the principal components bands and putting it back into color space. But this really highlights the colors, and so this is showing the really bright light tone material from these nodules. And so how did this stuff form? Well, there's actually kind of two opposing views on folks on the team. Some folks think that they were the result of volcanic fumaroles. So if you get volcanic fumaroles, like some of the places in Hawaii, they can produce very silica-rich deposits. But there's other evidence which seems to indicate there's like silica sinters. If folks have ever been to Yellowstone, some of the mud pots there, like we see here, are actually forming what we call silica sinters. And this is pretty exciting because very often with silica sinter deposits, they can trap biologic matter if there's any biologic matter to be trapped. So this is, and when this one reason for thinking that these might be silica sinters came from one of my colleagues on the team, a fellow Steve Ruff at Arizona State. He was working with the mini test data, and just for this example, looking at this rock here, and then the spectra from this mini test instrument. And so if you look at the green spectrum here, that's the rock, and then the red spectrum, or the other spectra are these silica sinter deposits, and these are actually different spectra than what you would get from a volcanic fumarole deposit. So it's more, at least from the mini test evidence, it's more consistent with the silica sinter deposit. And this is another one of these bright nodules, and this same colleague has found a potential analog for this on Earth up in it's a high altitude site in Chile called El Tatio. And so here some of these silica nodules near home plate, and here they are in this place, El Tatio. And they said they look very similar just from kind of a standoff perspective. And this is a microscopic imager image of these nodules from the rover, and then essentially the same resolution with some of these hand samples from this El Tatio place. And they both all have these kind of fingery, what they call digitate type of textures. And it turns out that these are actually what an astrobiologist would say is biologically mediated, that the little critters help form these little fingery type things. So, and if we had like a super high-powered microscope on the rovers, maybe we would have seen something like this. So these are like microfossils in a silica sinter, but we don't have that. So, are the things there, formed through biological processes? Well, we don't know, but it is actually going back to Gusev crater is one of the 3 finalists for the next big rover to go to Mars, the Mars 2020 mission. So we might get a chance to find out. Okay, I think I'm going to move on to opportunity. I'm going to get some water here. So, opportunity it's been incredible how long it's been going. We're in our 14th year of operation. It's just past solid 5,000 Martian days on Mars, and the mission success goal for both Spirit and Opportunity were 90 Martian days. So I mean, it's just incredible how long they've lasted. And this actually shows the traverse path. We landed in a small crater up here, Eagle Crater, and explored various craters here in the Meridiani Plains, and made our way to this giant 22-kilometer diameter crater, Endeavour Crater. And that's where we've been exploring since 2011, this rim of Endeavour Crater. And craters are important in the kind of surface exploration of Mars because they're probes of the subsurface. A crater meteorite will impact and dredge up material from deeper in the crust. And so, whereas the stuff that we've been exploring on the Meridiani Plains were, still very ancient. I mean, from a period in Martian history called the Hesperian, about 3.5 billion years ago. But the stuff that we're looking at here on the rim is from a more ancient period in Martian history, a period called the Noachian, which is about more like 3.8 to 4 billion years ago. So earlier in Mars's history. But the rocks that we're seeing initially on the Meridiani Plains turned out to be very, very sulfur-rich rocks, and this is just showing some of the color processing that I'll typically do with some of these multispectral images. So this is a rock that we saw very early in the mission, and then kind of doing this decorrelation stretch to make some of the clean surfaces stand out in purple, and it turned out to have a high, what we call a 535 nanometer band depth, which is a measure of how much ferric iron is in the rock, and so it's kind of very iron-rich rocks too. And this is a result from this Mossbauer spectrometer. It's an instrument that's sensitive to iron mineralogy, and as soon as we put the Mossbauer spectrometer down on some of these light-toned rocks there in Meridiani, we found the signature of this mineral jarosite. Jarosite is a kind of potassium or sodium bearing iron sulfate mineral. And if you drive up into the mountains here in Colorado and look at some of the mine tailings, some of them will look kind of yellow, so they're potentially jarosite in some of those things. But it was very significant because jarosite is always formed in the presence of water. So it was, right off the bat showing evidence of the action of water there in Meridiani Planum. The other thing that we saw right away were these things, what we called the blueberries. Initially, this is kind of a false color image. If you're looking at it in kind of true color, it'd look more gray. But in this kind of false color representation, they look blue, and these are little kind of ball-bearing sized spherules. It turned out to be very similar to a type of concretion. I'll show a picture in just a a little bit here, but it's, again, something that's formed by water kind of flushing through the rock and concentrating the iron into little concentration sites so it builds up spherules of iron. And this is a microscopic imager view of the blueberries. And what it turned out that these things were just kind of weathering out of the outcrop, so which kind of, again, lent more credence to this idea that they were this type of material called concretions, which are again formed kind of sedimentary or diagenetic features formed by water flushing through the rock and concentrating iron into certain sites. Another thing that's showing just very visibly how much iron is in the rocks happened when we would grind into the rock surfaces, because if anybody's done any kind of mineral identification class, one kind of way that you can identify minerals is by doing what's known as a streak test. If you take the back of a porcelain plate and rub a mineral against it, sometimes you get a color that's different than the visible color of the rock, and that's what we got here by grinding into the rock outcrop. We would get these kind of red tailings from the grind, which is essentially showing this very fine-grained red hematite, which is a Fe2O3, an iron oxide mineral. And this was confirmed using this Mossbauer spectrometer when we put that down on a concentration of these blueberries, showing the signature of the hematite. And the rocks themselves turned out to be a kind of sandstone, kind of ground up basalt, but they had been kind of washed in essentially an acid bath. It was a very acidic water environment, and very cemented by sulfur-rich materials. And a kind of analog potentially for how this formed, or like white sands. If anybody's been down to white sands in New Mexico, it's all formed from these gypsum sands, a calcium sulfate mineral, but it's all, even this big wide area of white sands is essentially blown out of a much smaller dry lake bed. And so we think that's how the stuff in Meridiani planum formed, that there was some kind of concentration of these sulfur-rich materials that were washed out over a wider area. And just again, some of these salt flats on Earth from Death Valley. And an analog for these, the blueberries are these things called, well, locally in Utah, they're known as Moki marbles. They're iron concretions that are can form in some of the sandstones. If you go to certain places in Utah or even western Colorado, you can find some of these things. So in driving with opportunity, we went over these very flat Meridiani plains. We encountered a lot of craters. This is a relatively fresh, small crater that we encountered early in the mission, and a bigger crater about, I think, about 190 meters across, called Santa Maria crater. But we drove across these a lot of the driving to get to that Endeavor crater was across these just very flat plains. So this is a panorama that we took called the Rub al-Khali panorama, which is, I think, a desert in Saudi Arabia. But the idea to getting to the rim of Endeavor crater, this is an orbital instrument called the CRISM, which is orbiting Mars, a compact reconnaissance imaging spectrometer for Mars that measures the reflectance spectra of rocks. And from this CRISM analysis of the rim of Endeavor crater, we're able to see clay signatures in some locations. And clays are important because, again, something is always formed in the presence of water, and also the type of clay mineral that will form will tell you something about the environmental conditions, the acidity of the water, and whether it's an oxidizing or reducing environment. Something that was kind of unexpected that we found on the rim of Endeavour crater was a bunch of veins. So this is, both of these are false color. This is a decorrelation stretch, highly stretched image of a gypsum vein. It turned out to be this mineral gypsum, a calcium sulfate, hydrated calcium sulfate mineral. And this is a picture of a gypsum vein that I took in Capitol Reef National Park. So very similar looking feature, and here's a microscopic imager view of one of these veins. So just as the concretions or blueberries formed by water flowing through the subsurface and concentrating certain minerals, the same thing with these veins. The way the veins typically form is that the subsurface waters will flow and leach certain chemicals out of the minerals, and then will reprecipitate them inside fractures. And so that's how these mineral veins formed. Something else that we found on the rim of Endeavour crater was another type of what we call a kind of boxwork kind of vein. It turned out to have chemistry consistent with a Montmorillonite clay, and this is kind of significant because I was just mentioning the fact that with the clay minerals you can typically tell about the environment in which they form. So for a Montmorillonite clay to form, that would have to form in kind of a relatively neutral pH environment, so that would be more conducive to the presence of life. And just a photo of terrestrial Montmorillonite. And just showing the long traverse path. So with the fact that actually opportunities like further down here now, but this one area that we reached with the rover we called Marathon Valley because it was it was a place where we had this relatively strong clay signature, and also we called it Marathon Valley because at that point the rover had driven the equivalent of a terrestrial marathon. It was at 26.2 miles, so it's pretty impressive. And this is just a view of Marathon Valley. We were driving south along the rim, so this is kind of this overlook looking down into the valley. And this kind of crater just outside the mouth of the valley gave one of my favorite panoramas, I think, of some basalt boulders forming kind of perhaps a dike in the middle, and then the various colored rocks around. And where we are currently exploring is we left Marathon Valley and went down to this another break in the rim of the crater called Perseverance Valley. And this is a digital elevation model showing this Perseverance Valley. And the thing that's significant here is because it's kind of a break in the slope, and from orbital imagery it looks like a channel that might have been carved by water, and it's a little hard to make out here, but it for folks who have the more keen geomorphology eye, you can see it does look a lot like a channel, but a very ancient channel formed early in Mars's history. And what we're currently trying to do with the rover is to try and understand if it was in fact formed by water, because in order for something to be a water-carved channel as opposed to something just like a dry debris flow, there'll be certain characteristics which we would be looking for, such as what's known as imbricated rocks in a channel. You tend to get rocks that'll kind of stack up in this kind of like domino fashion, and that's called imbrication. Or looking for some kind of perhaps sculpting into the rock, as you'll see sometimes if you go into some of the mountains, streams, you'll see kind of little holes that are carved into the rock by the flow of water. So we're trying to look for those types of things. One thing which we found recently, which is kind of unexpected, and this is just kind of a perspective view, is these stone stripes. There's a kind of a linear alignment of stripes that we see, and this is something on Mauna Kea, Hawaii, where you get a similar type of lineation occurring. And this is actually something that's formed by what's known as paraglacial processes, where you get water or water ice in the subsurface, and then it, I should have maybe put a cartoon in there, but it essentially forces the rocks into these linear stripe patterns. So it seems to be at least some circumstantial evidence for perhaps one of Mars's ice ages, because Mars actually has it orbits on kind of a high tilt, and so there are periods in its history when water ice kind of goes to lower latitudes, and so this might be some evidence of one of those kind of excursions with the ice coming to lower latitudes. But the opportunity is still going, and Congress and OMB willing, we can keep on going and keep on exploring. We're looking ahead and hoping to maybe go into the interior of the crater. We think that there are potentially evidence of more of these sulfate minerals which have stacked up, and also certain types of dunes which are seen across Mars which have never been explored. So hopefully we can keep on going. I'm going to talk a little bit about Curiosity. I'm not on the Curiosity team, but I try and keep up with what they're doing. Uh-oh, what happened? Oh, maybe we should do it. Okay, well. Sorry, my clicker is misbehaving. Maybe I just need to. Okay, see, when all else fails, whack it, and then that'll work. So, yeah. So this is an orbital view of Gale Crater. Gale Crater is about as wide across as kind of if you think of like Connecticut and Rhode Island put together, it's about as wide across as that. And this is the landing ellipse for Curiosity, and that's about where it landed. And the kind of goal, long-term goal of the mission is to head towards this giant mound, which is in the center of the crater, which is the formal name for it is Aeolus Mons, but everybody I think informally refers to it as Mount Sharp in honor of this fellow Thomas Sharp, who's a planetary scientist. And some of the, very early on in Curiosity's mission, it found evidence for ponding of water in the lower parts of the crater, because you can see some channels here, and I think that it ponded here. And this is just kind of a cartoon showing where the water is ponded. And some of the evidence for the flow of the water from from the walls of the crater were found early on in the form of conglomerates. Now, conglomerates is a type of rock that's formed from kind of a cobble-sized rocks and smaller. And in fact, Castle Rock, if you go down the actual castle of Castle Rock, is a conglomerate. Or if you ever hiked at Castlewood Canyon, that's all conglomerates. But this is a conglomerate that Curiosity saw, and in fact, this is an Earth conglomerate. And in fact, if I didn't have these labeled, you'd probably have a hard time telling which was from Earth and which was from Mars. But this is evidence of the kind of mass wasting of these materials from the walls of the crater to form these kind of poorly sorted but still somewhat rounded cobbles in the floor of the crater. And in fact, there are much finer grained materials which are consistent with lake bed deposits, mudstones, which are kind of a very fine-grained kind of sedimentary rock, which is typically something we see in lake deposits. And Curiosity has a drill, whereas with the Opportunity and Spirit, we had this rock abrasion tool for grinding into the rock. Curiosity actually has a drill, and so it'll drill into the rocks and then feed the ground up material into instruments in the interior of the rover. And one thing that you might point out here is just the gray color of it. You know, we think of Mars as being the red planet, but that's because all the surface materials have been so oxidized. In fact, if you dig down, most of the stuff that we see on Mars is really gray. And I should also mention, just with these these Curiosity rover pictures, the cameras that the Curiosity rover has are primarily just color cameras like you have in your camera. If you guys are familiar at all, they have these kind of a bare pattern filter. It's the same type of technology that's used in kind of commercial color cameras today. So it's more or less true color. And this is a nice view, you know, of looking towards Mount Sharp with some of the dunes and intervening features. And something that's really interesting with Curiosity that I think is kind of cool is just, I was pointing out the gray color, but not all these hills have, or drill holes have been gray. Here's this one which is more red, and it turned out there was more of this iron oxide mineral hematite in that material. And so this just shows the traverse of Curiosity from its landing point, and it's been gone a long ways past there, up to today. But this is, I think, just highlighting what I think are some of the cool discoveries from Curiosity. This one drill hole found evidence, and one instrument that Curiosity has that we didn't have with Spirit and Opportunity is something called an X-ray diffraction instrument. X-ray diffraction is a tool that we use to identify minerals based on their crystal structures. So this is an X-ray diffraction pattern, and it found evidence of a mineral tritomite, which is a kind of a form of quartz that's typically formed in kind of violent volcanic eruptions, like, you know, think Mount St. Helens. And what's really significant about this is that it's indicative of more silica-rich volcanic eruptions, whereas most of Mars is made of basalt and iron and magnesium-rich rock. This provides some evidence that perhaps early in its history there were more silica-rich volcanic eruptions. Curiosity also explored a dune field. This was the most intense examination of a Martian basaltic dune field. That was an orbital view. And this is a kind of a selfie that Curiosity took on the dune field. It has a color camera on the end of its robotic arm, so they're able to stick it out and kind of look back towards the rover and take the kind of selfie images of the rover. But these Bagnall dunes. Bagnall was a geomorphologist who did a lot of work on terrestrial dunes. And just another kind of pretty picture of the Bagnall dunes. And so, as Curiosity has kind of started climbing the slopes of Mount Sharp, and whereas initially early on in the floor of the crater it found some evidence for ponding of water, it's found much more evidence for the action of water. And so it turns out that we think that probably there were actually a series of lakes which formed inside of Gale crater, and in fact they might have been pretty extensive lakes. They're very deep enough for folks, if there are any fishies around, they could have swum around in there, but I don't know if there are any fishies around. So, some of the evidence for this comes from these layered sedimentary rocks. And in fact, we see some of these more fine-grained sedimentary rocks which show kind of cross-bedding, which is evidence of current flow. So if you think about shallow lakes, the winds will blow the lake currents around, and this will cause this type of cross-bedding pattern like we see here. And also with Curiosity, they've seen a lot of veins. I was pointing out some of the veins that we've seen with the Opportunity rover. Curiosity has been like seeing veins on steroids. I mean, really big veins. Again, calcium sulfate minerals, primarily, I believe. And I mentioned before that we think that there was probably a series of lakes that formed and then dried up and then reformed. And when we think of lakes drying up on the Earth, then they would, or even just a puddle drying up, in your backyard, it'll leave mud cracks. And in fact, we found some fossilized mud cracks with the Curiosity rover, so that's pretty cool. And that's something that excites me as a geologist, and most people, it's like two different types of rocks. But I mean, I think this is kind of cool that these two different formations here. These are the more lacustrine sediments, lake-formed sediments, and on top of it is another formation called the Stimson sandstone, which are probably Aeolian-formed, wind-formed dune deposits. And where Curiosity is now, I think it still is there, it headed towards this ridge, which was originally known as hematite ridge because orbital remote sensing indicated it was very rich in this iron oxide mineral hematite. And it was then renamed Vera Rubin Ridge. I can't tell you who she was. But so here's up on Vera Rubin Ridge, and they have a brush on the rover, and so brushing into it again, it looks very red, which is what you would expect with hematite. And in fact, some reflectance spectra from this spot shows a good hematite signature. So what's next in terms of Mars exploration? There are a couple more rovers that are going to Mars. Essentially, a duplicate of Curiosity is going up there, being launched in Mars 2020, but it has a different instrument payload. And the Europeans are sending a rover as well, which is pretty exciting. It's going to have this, Curiosity has this drill which will go, about several centimeters into the rock. This rover that the Europeans are planning on sending has a drill that'll go, I think they're going to try and go down like 2 meters or so. So it's pretty exciting. But that was my presentation. Yeah, so happy to take all the questions you have here. Yeah, Dina. Yeah.
A couple of things. First of all, I noticed there was no mention of any tectonic activity, which is not a surprise. But is that something that they have found? And then secondly, the hint of possible biologic activity, what specifically is going to explore that?
Okay, well, with regards to tectonics, we think Mars is essentially a one-plate planet. The plate tectonics never really got going on Mars. There's some evidence, and it's a little controversial. This orbital spacecraft, the Mars Global Surveyor, had a magnetometer and did some very low passes in its initial aerobraking, and it found some evidence that some people have interpreted as being maybe abortive plate tectonics very early in Mars's history. That's not really clear, but all the evidence seems to indicate that, for the vast majority of its history, it's been a one-plate planet. And with regards to trying to find out whether these silica-rich nodules at home plate, if Gusev Crater is in fact selected as the landing site for the Mars 2020 rover, the Mars 2020 rover is actually going to carry what's called a catching CHING system for collecting samples, and then kind of like if I'm out in the field and doing field work, I'll collect a sample and I'll put it into my backpack. It's essentially doing that, and so it's going to collect these samples, and maybe we'll send something to collect them later. No, I'm serious. I mean that's kind of where it's at, but that's it. Okay, yeah, Dan. Yeah.
When did volcanic activity end on Mars? Do we know?
Oh, well, I mean, we don't know that for sure that it's completely dead, but I mean, there are some things which we think are at least a few tens of millions of years old. Yeah.
What kind of, did any of the rovers do any measurements of the magnetic field of the rocks? Is there any magnetic field?
No kind of surface magnetometers have been carried to the surface. That InSight lander, I mentioned that very briefly. Is that gonna? I think that's going to have a magnetometer. I'm not 100% sure of that, but I think it's more of a geophysics related mission. But that might have. I'm not 100% sure of that. I know it's going to have a seismometer on board, which will be exciting. Yeah.
I've seen a couple pictures from back from the landers that show meteorites that can be captured.
Oh yeah. There's some folks on our team where like they get really spun up by that, and then there are other people on the team who say, "Oh no, not another meteorite."
Yeah, we have the same problem here.
That's leading to the question around the larger craters that have been explored. Did the rovers look for any evidence of meteorite impact debris? For example, like the nickel iron spherules around Meteor Crater in Arizona that formed the condensation into the impactor. Did they look for anything like that?
Well, I mean, the problem is that most of the stuff that craters that we've visited have been, eroded by the wind, and so eroded way down. So I think any kind of bits of impactor would probably be gone. With the types of meteorites that we've seen, there's been. I'm not sure what they've seen with Curiosity. With Opportunity, we've seen nickel iron meteorites. And we've seen stony iron meteorites. And the stony iron meteorites are actually seem to be kind of, if you think of the tektite strewn field where they'll get, because we saw actually a bunch of these, we saw them initially at this Endurance crater that was explored early on with Opportunity, and then we saw around this larger Victoria crater that we explored, and saw a number of these. So. But those weren't from the actual, crater-forming impactor. They were things that kind of broke up in the atmosphere and got kind of strewn across the surface. Yeah.
Were those calcium sulfate dihydride crystals?
Well, it was the stuff that we've seen with Opportunity. We think is primarily gypsum, which is here. I get to put on my nerd hat and do the chemical formula: CaSO4.NH2O. So it's like hydrated calcium sulfate. And the X-ray diffraction instrument on the Curiosity rover and some of the veins that they've examined have found anhydrite, which is just CaSO4 without the water, and also a mineral basanite, which is CaSO4 with just a single water molecule.
There was a lot of that.
Oh yeah. Yeah, in the back of them. Go towards the poles, is that what you said? No, they're not initially. Well, there was one mission, the Mars Polar Lander, which landed at high latitudes, and it dug down, and there was ice right near the surface. In terms of actually landing on the polar caps, folks have talked about trying to do that, but there's no hard plans for that. Yeah.
Is there any capability and need for communication between the rovers?
Well, they like to gossip amongst one another, but no, what they do, they communicate with the orbiters. That's actually how we get the data back from them. We have very limited kind of direct to Earth transmissions, but most of the data that we get back, the data is transmitted to one of the orbiters. It's stored on the orbiter, then it's retransmitted to Earth. So it's with the orbiters. Yeah, I mean, there's really no need for the rovers to talk to one another, unless they really want to diss one another. Yeah.
Home plate for Spirit and stuff, is that geothermal activity thought to be driven by the interior heat of Mars, or that's not like a central peak of where the impactors have been having visually?
Well, I mean, that's a good question, and I guess not a problem. Most likely, I would think kind of geothermal heat from the interior, but it is thought that associated with some of the impact craters that there are short-lived hydrothermal systems. But I don't think that's really thought to be the thing that caused the stuff that we saw there at home plate. I think that's probably more of a geothermal system.
Would the potential for geothermal systems to still be driven with that with Mars's water will stop out of
Yeah. Yeah. I mean, we've had there was this Mars thermal emission spectrometer and a thermal emission imaging system, which were trying to see if there were any kind of hot spots, and didn't find any. I mean, but as with a lot of things with Mars science, there's you have some evidence supporting one idea, but then some evidence which kind of goes against it. Because I mean, you might have read about some of these, what we call recurring slope lineae, which look like they're water kind of breaching the surface, and for water to be existing, it probably has to be heated somehow. But as I say, with the orbital thermal emission systems, we didn't really see any evidence for heating, and it was I kind of maybe got distracted. Did I answer your question? Okay. Yeah. Well, I try not to talk with the atmospheric science people. Mars it's a pretty uniform atmosphere. I mean, you might have read some about this idea that there might be methane releases in the Martian atmosphere, and that's very controversial. It's not really locked down. I mean, if it does exist, that is heterogeneous from different places, and if it is there, it's not really clear where it's coming from. But other than that, it's fairly homogeneous in terms of the gases making up the atmosphere. Because Mars does have weather. I mean, it has dust storms. It does even very thin water clouds, but in terms of the kind of the gaseous composition, it's pretty well mixed. Yeah.
So you haven't found the cows yet?
No cow methane. Yeah. Yeah. All right. Well, if that's in, thanks very much for being a great audience, and thanks for the invitation.